A question you might have at this point is, why does it work? So why are the samples that we drew using the acceptance rejection method actually following the distribution that we originally want to sample from? Let's see a proof for this. We want to show that the accepted y's using acceptance rejection method and the original distribution we want to sample from, x, actually follow the same distribution. To show this, it suffices again for us to show that y given accept and x have the same CDF. So what is the CDF of the y's given that they are accepted? By the definition of CDFs, we know that the CDF of y given accept of a constant x is equal to the probability that the random variable y is less than or equal to x given that y is accepted. Now, let's apply the Bayes rule. This is equal to P of accept, the probability of acceptance given y is less than or equal to x, times the marginal probability that y is less than or equal to x, divided by the marginal probability that a sample is accepted. Now let's look at the numerator. The numerator is a joint probability of two random variables. One random variable y and one random variable that's an indicator of whether we accept or reject. So by the definition of joint probabilities, the numerator is equal to the integral from negative infinity to x, because we want y to be less than or equal to x, of p accept given a constant y times g of y, the density of y, dy. And let's take a look at the denominator, and that should look familiar to you. We know that the marginal probability of acceptance is equal to 1 over c. So we can replace the denominator using 1 over c. Now, this part in red, p accept given y, should look familiar to you. You can go back to the earlier proof that the acceptance rate is equal to 1 over c and try to verify this. So in the next step, we pull this constant out, and then inside this integral, we replace p accept given y by the probability that u is less than this ratio we want to test for a given y value. And the rest is the same. So integral from negative infinity to x p of this thing times gy dy. And because we know that the uniform CDF is equal to this thing inside the parentheses, we can replace the red part again by fy divided by cgy. And the rest of it is the same. Now we can see that, again, the numerator, or like over here and on the denominator, there are gy's that can cancel out. And this thing equals just the integral from negative infinity to x of fy dy. You see that here's another constant we can pull out. And there's a c times c, 1 over c. So that becomes 1. So this becomes this. And let's take a look at what this is. This is actually just the definition of the CDF. So the integral from negative infinity all the way up to x of small f is by definition equal to large F of x. In other words, this is the CDF for the random variable x. So we have shown that the probability, there's a typo over here. This should be fx of small x inside. We have shown that over here, the CDF for y given acceptance, so the accepted y's, and the CDF of x are the same. In other words, these two follow the same distribution, and the samples that we accepted in this way indeed have the same distribution as the original x's.